Okay, roll.
Pairing still.
Oh, still pairing? That's right.
Oh, it's controlling this side.
The focus has to be on that, yeah.
How about now? Now still controlling this. Let me just close all this. And now?
Okay. Action.
Sit down.
Alright, so...
You have the microphone?
Yeah, where's the mic?
Oh, it's on the side.
So we're Adapt, formerly Motion. My name is Danilo Lacayo.
My name is Sergio Villa.
I'm Howard Tong.
And I'm Esteban de la Torre. So, for those of you who do not know, Adapt is a new product that focuses on using motion gestures to be able to control your computer. So for our application, we used it to be able to manipulate through PowerPoint slides, but the ultimate goal was to be able to perform more commands than a simple clicker would, because you have a finite number of buttons on that remote.
Alright, so how does it work? So it's pretty much, this device has 3 sensors on it. The first and most important one is the gyroscope that detects angular velocity. And what we do is we integrate it so that when you rotate it at some X direction or amount of angles, it gives you that amount of angles. Same thing with the moving it at a certain angle in another direction, and when you do that you get the orientation for it. The only problem is that the device is not aware as to which direction is up or down. So what we did was we included the second sensor, which is the accelerometer, which uses the gravity vector, which is acceleration or linear acceleration, and with that we're able to anchor the device so it knows which way is up and down, and the device from that point will now know which direction is left or right. But that's why we include the third sensor, which is the magnetometer, which will tell you which direction is true north. Let me play the video. And I mean, you guys seen this video before. It's demonstrating the. Did you click on it? Well, you'll be seeing in the other video, but it's pretty much a demonstration of the simulation we did on MATLAB when we were collecting the data to move it around. So. Oh. Alright, so this is the final design for our board. That is what is inside this device right now. So this device uses pogo pins to program the device. Pogo pins are these spring pins that are placed on a separate board, and they have springs on them, so it makes full contact to the bottom pads of the device that's located right here. And with it, we're able to remove header pins that were originally used to program the device, and now we were able to drastically reduce the size of the device. You
guys have one to pass around?
No, well, it's in a lab somewhere.
So here's our enclosure. It's pretty simple. We have it so that you can connect it to any watch band that's 20 millimeters. It's, like I said, fairly simple, perfectly encases the device. Yeah, it's the enclosure. So our state machine is very, very simple. We start in sleep, and then when data is ready and the FIFO gets full, we update the orientation, and then the data sent, goes back to sleep. So it's constantly going back and forth to sleep and updating the orientation.
So this is the communication diagram. It's relatively simple. The three sensors, the gyroscope, magnetometer, and the accelerometer, will be sending information to the PSOC through I2C, and the PSOC will be communicating with our laptop or cell phone through BLE, and it'll be sending data to just send whatever command we want it to do.
As for the power analysis, this time we went a lot more in depth than what we have in the past. So in order to calculate what percentages we had spent in the different states, we set a timer that initiated at the beginning of sleep mode, and once it came out of it, we stopped the timer. So using that little test, we were able to see that sleep mode was used up 73.5% of the time, and the rest of the time was inactive. So in active mode, this is when the three sensors are running, the PSOC BLE is running, and Bluetooth is also transmitting. So what takes up the most current is the PSOC BLE transmit. It did seem weird in the past showing that value, but on the data sheet, it shows that the transmit takes up that much, 15.6 milliamps. So doing that and adding all the powers and multiplying them by their ratio, with a 105 milliamp battery, we were able to calculate that the device lifetime is 9.85 hours.
So this is our bill of materials. The components that cost the most would be the PSOC, as well as our total amount of passives and power. And if we buy one, we would get it for $34. And for 10 is $31, and for 100 is $23.
But you want to sell 1,000, right? And then four will go down to 56.
We ran out of space.
Yeah.
This is a significantly long video. It's pretty much a documentary about our whole.
It's less of a marketing video, more of a...
Okay, good. Show it. You Sergio's head or stop? His eyes.
Oh, you need to upgrade your computer.
Full screen it too?
Alright, so I'm working.
You gotta do like 240p.
Oh yeah, lower the quality. Oh.
You want me to try my laptop? See if it's faster.
Try the internet, you just use the slowest application.
That's not the laptop.
It's the room. It's got bad reception.
A lot of magnetic fields in there.
A lot of magnetic fields.
Ever since we built a laser piano here, it's just been cursed. Goes to me.
I just for the most part, we've been working with the break up the three sensors and actual final our device. Oh yeah, recorded. So I've been doing the software all on EagleCAD.
Currently I'm working on the drivers right now for the three sensors. I'm just looking through the data sheet of the gyroscope right now, looking at the register value values and seeing which ones to write functions for, and be able to change the settings on the functions or the sensors themselves.
So our board just came in. That we ordered 2 weeks ago, and I was trying to solder it right now, and hopefully it works.
No sentence better describe this class. No sentence better describe this class. That'd be nice. Hopefully it works.
We had a person a few years ago, her name was Hope, actually, and she works at TI, right?
And she works.
After that, you know.
There was
What was that? You know about it?
Oh, I said after that there was no hope.
One of the major issues we were having was collecting data from the sensors. So the idea was that we have the sensors collecting the raw data to its internal file buffer. Once it reaches a certain threshold, it will then send an error telling the processor to extract the data, calculate it, and then go to sleep. While all this is happening, the sensors will continue to collect data, and this is a lot.
Right now I'm working on sensor conversions. We're essentially taking the raw data from each of the sensors and from there converting it to their intended units. So for the accelerometer it would be converting to meters per second, gyroscope would be degrees per second, and the magnetometer